Let's go to the gas phase and let's see what happens if we have a gas phase reaction and X is not my preferred variable. For gas phase reactions, it is preferred to express the mole balance equations in terms of number of moles or molar flow rates. So if you're not going to use X, so you might want to use Ni or Fi. Okay? Why not concentration? Why not concentration? Any idea? Well, let's look at the concentration equation. Okay, so let's take Ca for instance. Ca equals Fa over epsilon, right? Okay, so let's take this packed bed reactor. And this packed bed reactor is full of particles. Tamam. However, the catalyst here is deactivated, so the reaction will not take place. So let's see. Ca naught should equal Fa naught over epsilon naught, correct? Okay, and let's look at Ca at the end. Here we said that there is no reaction in this packed bed. Okay, just assume there is no reaction. So it will be Fa over epsilon, correct? And because there is no reaction, so Fa equals Fa naught. Again, we don't have reaction here. No reaction. Right. So it's a packed bed. When the flow goes through the bed, what do you think will happen to the volumetric flow rate? What will happen to the volumetric flow rate? Well, obviously, since it's a packed bed, the flow will experience pressure drop. So the pressure will reduce, the volumetric flow rate will increase, right? The volumetric flow rate will increase. So epsilon will be greater than epsilon naught. And what happens to the concentration? The concentration will drop. But did it drop because there was a reaction, because A was consumed? No. It did not drop because A was consumed. It dropped because the volumetric flow rate changed. Because on gas phase, because the volumetric flow rate is very sensitive to the temperature and pressure. Okay. So, and of course the total number of moles. So we don't use concentration to monitor the progress of the reaction in a gas phase reaction, because C concentration could change without even the moles or the molar flow rate changing. Okay, so therefore I prefer to deal with either number of moles or the molar flow rate. طيب, so let's apply the design algorithm to this system, reactive system. We have an elementary gas phase reaction in a plug flow reactor. I have A plus 2B goes to C reversibly, the reaction is reversible. And let's see, the algorithm starts with the mole balance. We can write the mole balance in terms of X or in terms of Ni, Ci, Fi, right? Okay, this part we said X for some reason is not my preferred variable, so let's try to use the other three. Which one are you going to use? Are you going to use Ci? Nope, you're not going to use concentration, because concentration is a bad indicator to measure the progress of a reaction in a gas phase system, right? Because simply the volumetric flow rate could change for reasons other than reaction. Okay, so I'm not going to use Ci. Are you going to use Ni? No, it's a plug flow reactor, continuous flow system. I'm not going to use number of moles. I'm going to use the molar flow rate, Fi. Okay, so let's write the design equation in terms of molar flow rate. Okay, so here's my design equation. here's my design equation, and maybe it's not clear. Let me write it, circle it in a better way. Oops, there we go. Okay, so this is the design equation. dFA over dV equals RA. So I wrote the mole balance. When I wrote the mole balance, RA now is variable, right? So we need to provide an equation for. So we provided the equation for RA, which is known as the rate law. So we're done with step number 1. We go to step number 2, rate law. It's all by logic. Minus RA equals KA times CA times CB to the power 2 minus CC over KC. It's a elementary reaction, so I don't need to derive the rate law. I just can write it right away. Okay. Fine. So let's see. Now we are done with the rate law. Let's go to stoichiometry. When we go to stoichiometry, in this step, we know that we need to provide an equation for CA, CB, and CC. Why is that? Because when we wrote the rate law, we introduced 3 other variables, the CA, CB, and CC. Therefore, I need to provide an equation for these 3 guys. Let's start with CA. Let's start with CA. Right. So CA equals FA over epsilon. What does FA equal? Do I write FA equals FA naught 1 times 1 minus x? No, I don't, because we said x is not my preferred variable. So I'm just going to leave it as FA. Okay, what about epsilon? Well, epsilon, it's a gas phase reaction. Remember, the first thing you ask yourself when it comes to epsilon, you ask yourself which phase is the reaction in. So it's a gas phase reaction. So I can use the equation of state, right? Okay, so epsilon equals epsilon. Oops, why does it keep changing? Anyway, epsilon naught times 3 correction factors, right? What are these correction factors? Well, the correction factors are as follows: the number of moles, right? The total number of moles, the correction factor for the temperature, the correction factor for the pressure drop. Okay, so let's write these correction factors. So epsilon equals epsilon naught times Ft over Ft naught, right? Because if total number of moles increases, the volumetric flow rate will increase. Then a correction factor for temperature, T over T naught. Then the correction factor for pressure, which is P naught over P, correct? P naught over P. So let's simplify this equation. Well, it's a plug flow reactor, so this guy is almost 1 because we are assuming negligible delta P. Okay, what about T over T naught? Again, it's isothermal operation, so this goes to 1. So I'll end up with epsilon naught times Ft over Ft naught. Let me rearrange the equation. So Ca equals Ft naught over epsilon naught times Fa over Ft. Okay, and what does Ft naught over epsilon naught equal? Well, it equals Ct naught, correct? It equals Ct naught times Fa over Ft. Fa over Ft. So now we have an equation for Ca, okay, which is, okay, I'm gonna write it up there, maybe so that it will be clearer to you. So we have Ca equals Ct naught times FA over FT. Okay, so I wrote an equation for CA. Okay, and I related CA to FA. Is this something I really wanted? Yes, that's what I wanted, because let's see, the rate law is given in terms of concentrations, right? CA. However, if you substitute this equation here, now the left hand side will be written in terms of FA, and the right hand side here will be written in terms of CA. So I do need an equation. I do need an equation which relates to me the CA to FA. I do need that. Okay, and this is something I did here. Tamam? Okay. So that was really a useful step. Let's look at this new equation which I provided. Does it include a variable? Did I introduce another variable? Yes, I did. Yes, I did. You can see that I have introduced ft, and ft is a variable. Ft changes as you go down the length of the reactor. Therefore, we need to provide an equation for. What's that equation? Very simple. Ft equals Fa plus Fb plus Fc. Tamam. Do you have inert? If you had inert, you will say plus Fi. Okay. Now we have an equation for Ft. We had to add it, right? Right. What about Fa? Is it a variable? Yes, it's a variable, but I have an equation for, right? See, this is the equation for Fa. But what about Fb and Fc? They are also variable. That's why we need to provide equation for as well. This is a design equation for B, and this is the design equation for C. So again, the logic tells me that if I have a gas phase reaction and I'm going to write the design equation in terms of molar flow rate, not in terms of X, you will end up needing to write the design equation for all the involved species, right? For all the involved species. Okay, and this is something we have mentioned at the beginning of the lecture. When we use X, we will need only to write one design equation. Okay, tamam. So we have Fa naught dx by dv equals minus Ra. That's it, one design equation. But if I'm going to use molar flow rate or concentration or number of moles, I might need to write more than one design equation. In this case, it's very obvious why we have to write the design equation for all the involved species. Okay, so that means I will end up with, as you can see here, RB and RC. However, in the rate law step, I only defined RA, right? I only defined RA. So how are we going to find RB and RC? Yes, you're going to use what? Stoichiometry. I'm going to use stoichiometry to do this. So in the stoichiometry step, I'm going to use the stoichiometry to relate all of the rate of reactions. And you know how to do this, right? So simply you write RA divided by minus 1 equals RB divided by minus 2 equals RC divided by 1. Okay, and from here you can write all the relationships. So you can say, well, simply RB equals 2 times RA, and RC equals minus RA. So we have some relationship here between the rate of reactions. Okay, to summarize, in the stoichiometry step, you might end up writing sub-steps. The first step is to relate the reaction rates together, The second step is to write the concentration as a function of molar flow rate using the basic definition of Ca. When I do this, I might introduce other variables like T, right? Like T could be a variable. So what do? You provide an equation for T using the energy balance. We'll come to this in chapter 8. What else could be variable? P could be variable. So that means you need also to provide an equation for P, which is the Ergen equation. What else is variable? Well, if T might be variable, not necessarily, of course. If the stoichiometry is all 1-to-1, the delta is 0, total stoichiometric number is 0, then Ft will remain the same. So Ft will equal Ft naught. However, if Ft is changing because the stoichiometric numbers are different for the different species, or the total stoichiometric number is not 0, then Ft changes. Therefore, I need to provide an equation for Ft. Tamam, which is Ft equals the summation of all of the Fi's. Okay, so you understand the logic and you know how to proceed. Tamam? And then of course we're going to do combine and evaluate using the software. Of course, the software you don't need to use the combine with hand calculation and evaluation. The software will evaluate the equation, but you need to evaluate the parameters or ask the software to evaluate the parameters for you by using explicit equations. طيب, let's take another example. Where x is not my preferred variable and I'm going to use the molar flow rate. So this example is related to a design of packed bed reactor for the reaction A moles of A plus B moles of B gives you C moles of C plus D moles of D. Okay, the algorithm consists of 5 steps. We're going to start with the mole balance. What does the mole balance say? It is dFi by dW equals Ri prime, right? And how many equations you're going to write? Yeah, you're going to write 4. 1 for each of the species, right? So I'm going to write dFa by dW equals Ra prime. dFb by dW equals Rb prime, and so on. Type. Next comes the rate law. How many rate law are you going to write? Obviously 1. You have 1 reaction, 1 rate law. So let's assume this is the rate law. Then we go to stoichiometry. In the stoichiometry, you'll need to provide many informations. The first information is to relate the rate of reactions together, right? Because in the mole balance, we have 4 mole balances and we have all the rate of reactions, Ra, Rb, Rc, Rd, and so on. So you're gonna, the first step in the stoichiometry, step A, if you want to call it, you're gonna utilize this relationship between the rate of reactions, and you're gonna write 3 equations, right? One for Rb in terms of Ra, second one is for Rc, the third one is for Rd, and remember they are all in terms of Ra. Right. Next, in the stoichiometry, we're gonna write an equation for Ci. Yes, we're gonna write an equation for Ci. So let's write an equation for Ci. So Ci equals Fi over epsilon. What about Fi? Fi remains as Fi because my preferred variable here is the molar flow rate. I don't want to change it to x. What about epsilon? Epsilon equals epsilon naught times the 3 correction factors. The first one is related to total number of moles, right? The second one related to temperature. Third one related to pressure. Thank you for helping me. Okay, and upon simplification, you get this equation. You'll get this equation. طيب. So when I wrote this equation, did I introduce other variables? Obviously, you did. Is CT not variable? No, it's not. Is Fi variable? Yes, it is. But no worries, we have equations for Fi. Is Ft a variable? Yes, it is. Right? Yes, it is. Okay, or it could be actually. If it's a variable, then you write an equation. You provide an equation for, right? Okay, so before we move forward, just wanted to tell you, okay, how many equations we're gonna write for CI. Obviously, we could write 4 equations, right? CA, CB, CC, and CD. However, if you look at the rate law, you'll see we only need CA and CB. So 2 will be enough. We don't need to write 4. Okay, let's go back to our variables. So we were talking about Ft. So Ft is a variable. Then we need to provide an equation. In this case, we'll have Ft equals Fa plus Fb plus Fc plus Fd. If you had an inert, you also add plus Fi. Type. What else? Temperature. Well, if it was a variable, then you have to provide an equation. dt by dw. Where are you going to find it from? The energy balance in chapter 8. Not now. In this case, T is constant, isothermal operation, so T naught over T goes to 1. Okay, what about Y? Y, well, it's a packed bed reactor, so the pressure is dropping, right? The pressure is changing down the length of the reactor, so it is variable, so you need to provide an equation, صح? And where is it coming from? Yep, it's coming from Ergen equation. And as you can see, we chose the Ergen equation, which is written in terms of molar flow rate rather than in terms of conversion, because conversion is not my preferred variable. Tamam? Okay, and then you're gonna combine and evaluate. Actually, you're gonna, if there is a parameter to evaluate, you're gonna evaluate it. Otherwise, you're gonna ask let the software do the combination and the evaluation for you. Type. With this, we reach to the end of today's lecture. Thank you for listening, and we'll meet soon.